Have you ever been cruising down the highway on a long road trip and you just kind of glance down at your car's dashboard? Looking right at the temperature gauge? As long as that needle is sitting right in the middle, steady and calm, you literally don't even think twice about it. But the second it creeps into the red, panic sets in, right? Your engine has a specific, safe baseline. But what about massive industrial plants? Those towering refineries or sprawling chemical facilities? Just how hot does that colossal industrial equipment get on a normal, steady day? And really, how do the engineers building these megastructures even define what normal means? Well, welcome to this explainer. Today we're going to unpack a deceptively simple metric that dictates exactly how industrial giants are built, wrapped, and painted in the EPC industry, which stands for Engineering, Procurement, and Construction. Section 3.3.1, Operating Temperature, the heartbeat of plant equipment. Let's dive right in. Now, you might be thinking, it's just a temperature reading, how complicated can it really be? But in the world of plant engineering, this specific metric is essentially the heartbeat of the equipment. Without a firm grasp of it, the entire engineering process would completely stall. No pipes get laid, no tanks get built. So, what exactly is it? Operating temperature is formally defined as the maximum temperature reached by equipment during normal operation. Now, I really want you to focus on those two words right there, normal operation. This isn't just some random average. It's definitely not a guess. It is the absolute peak heat that a vessel, a tank, or a pipe is going to reach while doing exactly what it was designed to do, say on a perfect, typical Tuesday afternoon. Think of it as the baseline, normal heartbeat of the machinery. It's the predictable, intended thermal state of whatever chemical or physical process is flowing inside.
And honestly, this brilliantly illustrates why that definition has to be so incredibly strict. We literally have to draw a hard line between normal operation and abnormal situations. The operating temperature metric strictly belongs to the intended process, meaning everything is going exactly right. But what happens if an operator makes a mistake? Or what if there's an unexpected chemical reaction, a sudden power failure, or just a completely unpredictable spike in heat? Well, that falls entirely into the abnormal category. The operating temperature absolutely does not account for human error or sudden emergencies. It's a strict boundary condition that assumes the whole shebang is going exactly to plan.
Okay, so let's see how this actually builds into the human workflow at an engineering firm. How does this critical number get passed around between teams? It's basically a highly structured relay race. It starts at step 1 with the process engineer. They're the ones designing the chemical or physical reactions, so they calculate what that normal maximum temperature is going to be. Then, moving to step 2, they log this official number into a master document called the equipment data sheet. Finally, in step 3, the mechanical engineer, the person actually designing the physical metal vessel, takes that data sheet and applies the number. But here's where things get kind of crazy for beginners. Take a look at this. Mechanical engineers rarely use operating temperature for structural design. Wait, what? We just said this is the heartbeat of the equipment, right? So why in the world wouldn't the person building the metal tank use the normal operating temperature to calculate how thick the steel needs to be? It's a massive misconception, and one that honestly trips up a lot of people early in their engineering journey. When mechanical engineers calculate the required strength and thickness of the metal to prevent it from bursting under intense pressure, they actually use a totally different metric called the design temperature. And that number includes a hefty safety margin for those abnormal spikes we just talked about. So yeah, they actually don't use the normal operating temperature for structural strength calculations at all. Which brings us to a pretty massive question. If the mechanical engineers are just ignoring this number when calculating the strength of the steel, what is the operating temperature actually used for? Why does the process engineer spend so much time calculating it, and why does it have this dedicated, highly guarded spot on the official equipment data sheet? It feels like a bit of a mystery, right? Well, it turns out that this normal heartbeat dictates the external survival and safety of the equipment in two absolutely crucial ways. Let's take a look at the first one. Imagine a massive metallic vessel being wrapped in thick, yellow external insulation. This right here is the first major real-world application of our metric. The required thickness and the material of this insulation are dictated almost entirely by the operating temperature. Because mechanical engineers know exactly how hot this vessel gets during its normal intended process, they can calculate exactly how much insulation padding is needed to wrap around the steel. It's literally like picking out the right winter coat based on the daily weather forecast. You wouldn't wear a heavy parka in the middle of summer, and you definitely wouldn't wrap a tank unnecessarily if it just naturally runs cool. But hold on, why are we putting a winter coat on a massive steel tank in the first place, especially one that might be running at like 200 degrees Celsius? It seems kind of backwards, doesn't it?
Well, it all comes down to two primary goals based on that baseline operating temperature. First up is heat conservation. If the process inside needs to stay incredibly hot to keep the plant running efficiently, the insulation prevents that heat from just escaping into the surrounding air. It maintains the intended process. But the second reason, that one is even more critical: personnel protection. If the data sheet says the operating temperature of a vessel is over 70 degrees Celsius and it sits in an area where humans are walking by, well, touching that bare metal would cause severe, instant burns. So engineers use the operating temperature to calculate exactly how much insulation is needed to keep the outer surface cool enough for human operators to work safely alongside it.
Okay, now let's look at the second major application here: paint specification. When you see those giant industrial plants, they're usually painted in various industrial coatings, right? Well, that paint isn't just for aesthetics. It's not just there to make the plant look pretty. It is a highly engineered chemical barrier. And the specific type of paint chosen, that depends entirely on the operating temperature. If you apply just a standard, run-of-the-mill paint to a vessel that normally operates at 200 degrees, that paint will literally peel right off within hours. The right paint specification has to resist thermal degradation and maintain those anti-corrosion barriers. Without knowing the exact operating temperature, engineers couldn't select the right paint, the metal would just rapidly rust from the elements, and the entire multi-million-dollar piece of equipment could literally fail from the outside in. So, as we wrap up this explainer, I really want you to think about those invisible thermal limits governing the machinery around you. The operating temperature isn't just some boring number on a page, it's the intended pulse of an industrial giant. Sure, it might not dictate the sheer thickness of the steel, but it absolutely dictates the skin of the machine, the paint that fights off rust, and the insulation that keeps the energy inside and the human workers outside perfectly safe. So, next time you drive past a sprawling refinery, ask yourself, what hidden heartbeat is keeping that entire metallic city alive right now? Keep asking questions, keep looking deeper, and we'll catch you in the next explainer.